To understand why this particular discovery has astronomers using words like exciting rather than their usual careful, clinical language, you first need to understand exactly what the habitable zone really is, and why so few planets ever seem to land inside it. Every star radiates heat and light outward in every direction, and depending on how bright that star burns, there exists a specific distance range around it where a rocky planet, if it has the right kind of atmosphere, could maintain liquid water on its surface, rather than freezing solid or boiling away entirely. Move a planet too close to its star, and any ocean it might have had gets boiled into vapor and eventually stripped into space. Move it too far away, and any liquid, water freezes into ice, locking away the potential for the kind of chemistry life on Earth depends on. This band, sometimes called the Goldilocks zone because conditions inside it are neither too hot nor too cold, but just right, is not a fixed distance the way it might be around every star. It shifts depending on the size, temperature, and brightness of the star in question, around a small, dim, cool red dwarf star. The habitable zone sits much closer in, sometimes within a distance that would place a planet well inside where Mercury orbits our own sun. In that detail, the fact that habitable zones around small stars are pulled in tight turns out to be central to understanding both the promise and the danger waiting for the planet at the heart of this story. That planet carries the designation GJ3378b, and it orbits a faint red dwarf star sitting in the constellation of Camelopardalis. The Giraffe, a dim and unglamorous patch of northern sky that most people have never had a reason to look toward. The star itself is nothing spectacular to the naked eye, one of the countless small, cool, red dwarfs that vastly outnumber stars like our own sun across the galaxy, quietly burning for tens of billions of years longer than any sun-like star ever could. But small and dim does not mean unimportant, and in 2024, a team of French astronomers using the Canada-France-Hawaii telescope on Mauna Kea in Hawaii detected something orbiting that faint red star, a planet betraying its presence not through direct imaging, not by blocking any starlight as it passed in front of its sun, but through something far more subtle: gravity. Here's how astronomers actually catch a planet they cannot see. A planet does not simply orbit its star while the star sits, motionless at the center, indifferent to its planetary companion. In reality, both objects orbit their shared center of mass, and because a star is so much heavier than any planet circling it, that shared center of mass sits very close to the star itself, but not exactly at its center. As a result, the star performs a tiny, rhythmic wobble, tugged back and forth by the gravity of the planet orbiting it. That wobble is far too small to see directly through any telescope, but it leaves a fingerprint in the star's light. As the star wobbles slightly toward Earth and then slightly away, the wavelengths of light it emits shift almost imperceptibly, compressing toward the blue end of the spectrum as it approaches and stretching toward the red end as it recedes, an effect called the Doppler shift, the same basic phenomenon responsible for the change in pitch you hear when a siren races past you and then fades into the distance. By measuring that shifting starlight with extraordinary precision, astronomers can calculate not just that a planet exists, but roughly how massive it must be and how long it takes to complete each orbit. When the French team first measured GJ3378b using this method back in 2024, their instruments told them the planet weighed in at 5.26 times the mass of Earth, a size that places a world firmly into what astronomers call mini-Neptune territory. Planets substantial enough that they likely hold on to thick, puffy atmospheres of hydrogen and helium, more closely resembling a smaller, rocky cousin of Neptune than anything resembling our own world. A planet that size, with that kind of atmosphere, is a fascinating scientific target in its own right, but it is not the kind of place anyone expects to find oceans, continents, or life. The 2024 discovery was filed away, respectfully, as an interesting but unremarkable addition to the growing catalog of exoplanets circling nearby red dwarfs. One more data point among the more than 6,000 exoplanets confirmed since astronomers first detected a world beyond our solar system back in 1992. It is worth remembering just how recent and how hard-won this entire field of study actually is. The very first confirmed exoplanet was found orbiting not a normal star at all, but a pulsar, the rapidly spinning corpse of a dead star. Discovered in 1992, a discovery so strange that many astronomers initially assumed something must have been misinterpreted, since nobody expected planets to survive the supernova that creates a pulsar in the first place. The first exoplanet found orbiting an ordinary sun-like star followed just 3 years later. In 1995 and 4 years afterward, each new detection was treated as a landmark event, worthy of front-page coverage. Now, 3 decades later, astronomers have cataloged more than 6,000 confirmed worlds beyond our solar system spread across more than 4,000 separate planetary systems. And what was once a field defined by scarcity has become a field defined by abundance. A genuine embarrassment of riches, where the challenge is no longer simply finding planets, but figuring out which of the thousands already found deserve a second, more careful look. Then, in 2026, a team led by Paul Robertson, an astronomer at the University of California, Irvine, decided to take a second, more careful look. And what they found rewrote the planet's entire identity. Robertson's team returned to GJ 3378b armed with 2 separate high-precision spectrographs. Instruments capable of measuring that telltale Doppler wobble with far greater sensitivity than the original 2024 observations had achieved, including data gathered using the WIYN 3.5-meter telescope at Kitt Peak National Observatory near Tucson, Arizona. When they reanalyzed the star's wobble with this sharper instrumentation, the numbers that emerged were strikingly different from what had been published just 2 years earlier. The planet's true mass, Robertson's team determined, was not 5.26 times that of Earth. It was 2.3 times the mass of Earth, less than half of what everyone had believed. That single correction moved GJ 3378b out of mini Neptune territory entirely and into an entirely different category of world. A genuine rocky super-Earth, a planet plausibly built from stone and metal rather than thick layers of gas. The kind of world where solid ground, and potentially liquid water sitting on top of it, becomes a real scientific possibility rather than a fantasy. But the mass correction was only half of the revelation. The same careful reanalysis also revised the planet's orbital period, the length of its year. Instead of the 25-day orbit originally measured in 2024, Robertson's team found that GJ 3378b actually completes a full lap around its star in just 21 days, a small difference on paper that carries an enormous consequence. A shorter orbital period means the planet sits closer to its star than previously believed. And when Robertson's team recalculated exactly how much stellar radiation that closer orbit would expose the planet to, the number that came back was almost eerie in its familiarity. GJ 3378b receives approximately 90% of the radiation that Earth receives from our own sun. Not a fraction of Earth's warmth. Not an overwhelming multiple of it. 90%, close enough that, in the right circumstances, with the right atmosphere, this small rocky world could plausibly host liquid water on its surface right now. Paul Robertson did not hide his enthusiasm when the revised results came in. "This one's exciting," he said, describing GJ 3378b as one of our closest cosmic neighbors. 25 light-years sounds like a long way, he explained, but the Milky Way itself stretches roughly 100,000 light-years across, meaning that in the context of our home galaxy, a star just 25 light-years away is, relatively speaking, next door. This super-Earth gets about 90% of the radiation from its host star that Earth gets from our sun, Robertson said, so it's right in the sweet spot. Sit with that phrase for a moment. Right in the sweet spot. After more than 3 decades of exoplanet science, after cataloging thousands upon thousands of worlds orbiting distant stars, the overwhelming majority of them either far too hot, far too cold, far too massive, or far too strange to ever host anything resembling familiar biology. Here is a rocky world sitting almost exactly where Earth sits relative to its own star, corrected into existence not by a brand new discovery, but by a more careful remeasurement of a planet astronomers already thought they understood. It raises an uncomfortable, fascinating question that applies to more than just this one star system. How many other planets currently cataloged as unremarkable mini-Neptunes, filed away and forgotten in astronomical databases, might actually be rocky, potentially habitable worlds hiding behind an imprecise first measurement, waiting for someone to simply look again with a sharper instrument? And yet, for all of this genuine excitement, there is a serious complication sitting at the center of this story, one that keeps even the researchers who found this world from declaring victory. The star GJ 3378b orbits is a red dwarf, and red dwarfs, for all their appeal as long-lived, common, easy-to-study stars, carry a dangerous reputation. Despite burning cooler and dimmer than stars like our own sun, red dwarfs are notorious for producing violent, unpredictable outbursts of radiation, powerful stellar flares, and gusts of charged particles known as stellar wind that can be far more intense relative to the star's size than anything our own calm, comparatively well-behaved sun produces. A red dwarf can erupt with flares carrying a far larger share of its total energy output than an equivalent flare from the sun. And because a habitable zone planet orbiting a red dwarf sits so much closer to its star than Earth sits to the sun, that planet absorbs the full, undiluted force of every one of those violent outbursts. It's over hundreds of millions or billions of years. This relentless battering of radiation and charged particles can slowly strip away a planet's atmosphere entirely, peeling it into space, layer by layer, molecule by molecule, leaving behind nothing but a bare, irradiated rock with no protection, no weather, and no water. This is precisely the uncomfortable truth facing GJ 3378b, sitting close enough to its star to receive. Earth-like warmth also means sitting close enough to absorb whatever violent tantrums that small, dim star throws in its direction. And astronomers studying red dwarf systems have already documented planets elsewhere that appear to have been scoured completely bare by exactly this process. Worlds that likely once sat in perfectly temperate zones, only to lose everything that made them promising. So does GJ 3378b actually have an atmosphere? Right now, astronomers genuinely do not know, and more frustratingly, they currently have no reliable way to find out. Here is why. The most powerful tool available to modern astronomers for studying a distant planet's atmosphere is something called transit spectroscopy, technique that requires the planet to pass directly in front of its star from Earth's point of view, blocking a small sliver of starlight as it does so. When that happens, some of the star's light filters directly through the planet's atmosphere on its way to our telescopes, and different gases in that atmosphere absorb very specific wavelengths of light, leaving behind a kind of chemical fingerprint that instruments like the James Webb Space Telescope can detect and decode. This is exactly how astronomers have begun probing the atmospheres of rocky worlds orbiting other red dwarf stars, including the famous seven-planet system known as TRAPPIST-1. But GJ 3378b does not transit its star from our vantage point on Earth. Its orbit is tilted just enough that it never crosses directly between its sun and our telescopes, which means the single most powerful atmospheric detection method available to modern astronomy simply cannot be pointed at this particular world. Not yet, not with any instrument currently operating, and not for the foreseeable future either. Instead, astronomers are looking ahead to the 2040s, when NASA hopes to launch an entirely new observatory purpose-built for exactly this kind of challenge, called the Habitable Worlds Observatory. Unlike the James Webb Space Telescope, which studies atmospheres primarily through the light that filters through a planet during a transit, the Habitable Worlds Observatory is being designed to directly block out the blinding glare of a distant star and capture the comparatively faint light reflecting directly off a planet's surface and atmosphere, even for worlds like GJ 3378b that never transit at all. If that mission launches successfully and performs as hoped, it could finally answer the questions sitting unresolved at the center of this discovery, whether this nearby, Earth-like world still holds on to an atmosphere after enduring however many hundreds of millions of years of its red dwarf star's radiation, or whether it long ago lost the fight and now sits bare and lifeless, a rocky shell with all the right conditions for life and none of the ingredients left to support it. James, a University of California Irvine student who worked alongside Robertson's team to characterize the planet's newly revised size, explained exactly why the atmosphere question matters so profoundly. If a planet in the habitable zone has a proper atmosphere, James said, we can justify further research looking for biosignatures, liquid water, or other signs of life that require both an atmosphere and the right amount of heating from the host star. In other words, an atmosphere is not a bonus feature on a potentially habitable world. It is the entire foundation everything else depends on. The layer of insulation and chemistry that could allow liquid water to persist at all. And the only medium through which any distant sign of biology could ever realistically be detected from 25 light-years away. Michael Endel, an astronomer at the University of Texas at Austin, who was not part of Robertson's team, but is closely followed. This expanding search for nearby habitable worlds framed the stakes in the broadest possible terms. The ultimate goal is biosignatures, Endel said. We really want to know, are we alone in the universe? We're still in the reconnaissance phase of our solar neighborhood, trying to find the planets around the nearest stars, because those will be the easiest ones to detect a biosignature on. This planet, he added, brings us one step closer to knowing all of our neighbors, and ultimately, which of them might be hospitable for life. The reconnaissance phase. That phrase deserves attention because it reframes this entire discovery within a much larger, quietly astonishing project that has been unfolding. For decades, with almost no fanfare outside the scientific community, humanity is not simply hunting for one lucky planet that might harbor life. We are conducting a systematic census of everything orbiting the stars nearest to our own, cataloging masses, orbits, temperatures, now increasingly, atmospheric compositions, star by star, planet by planet, patiently building toward the moment when our instruments finally become sharp enough to answer the oldest question human beings have ever asked while looking up at the night sky. Every ancient civilization that ever gazed upward and wondered whether the points of light scattered across the darkness were watching them back was, in some unformed way, asking the exact question modern astronomers are now